Ever wondered what this is? Some say it's brightness, others a modern tool for seeing, but it actually is just electromagnetic radiation. We see it every day when the sun comes up or when we flip a switch once it's dark. But what really constitutes the energy and essence of light? We knew that light oftentimes acted as a wave, such as when it hits one transparent medium and refracts in the other. This is light when it enters from the air into water. There's an angle of incidence and it results in a changed refracted angle of refraction. We knew this because of our prior knowledge on the behavior of waves, since they were altered by different mediums of travel. Sound, for instance, travels fastest in a solid compared to in a liquid or in a gas. Thereafter, in the 1800s, physicists were experimenting to see how exactly we can define the properties of light. Consider the double slit experiment. It was tested using a laser that emitted a light beam that resulted in a specific diffraction pattern because the light interfered with itself. Like a wave, therefore, it has a wavelength. Because there's a physical space between the peaks of the wave, it is a real physical wave. That's how ultraviolet light, infrared light, and visible light all appear in the electromagnetic spectrum with all the other waves. Although many experiments on interference, diffraction, and scattering of light revealed the apparent wave-defining properties of light, something didn't add up. No one could give a single mathematical formula for the observed distribution of the energy among the emitted wavelength. Under general light assumptions, light always acted continuously, as expected for waves. However, Planck mathematically derived a law that described the energy distribution as equal discontinuous parcels or quanta of energy. However, he didn't see the scientific implications of his work. No one did, not until a guy by the name of Einstein came along. Albert Einstein worked with the photoelectric effect, which later won him a Nobel Prize in physics. Let's take a closer look at the experiment. Let's say you have a metal plate. Metals have electrons that are attracted to the positive charge of the nucleus. Now, if you shine a light on the metal, depending on the frequency, you can knock out the electrons, which create a measurable electrical current. For example, in the photoelectric effect experiment, photons are emitted to hit the metal plate and therefore the electrons. If enough energy is present, the light can stimulate the electron to be released, creating a photoelectron. Since energy is conserved, part of the photon's energy was used to free the electron, and the rest was converted into kinetic energy. The stimulated electrons then are attracted to the positively charged side of the circuit, therefore establishing a current which allows us to measure the remaining kinetic energy. Now, the classical expectations, assuming light was a wave, were that higher light intensity leads to higher energy of electrons leaving the metal plate independent of frequency. The experimental results, however, saw that a threshold frequency was required to stimulate the photoelectric effect. Einstein's findings were that light, which was originally thought of as only a wave, can sometimes act as a particle or packet of energy. This directly led to the development and theorization of quantum mechanics. This is true because there exists a duality called wave-particle duality, in which light exhibits the qualities of being both a wave and a particle. This applies to other quantum matter such as electrons and all other forms of compound or elementary particles, since they too can exhibit wave properties due to interference patterns. Why is any of this physics important? Well, for one, quantum mechanics has explained the structure of the atom and the nucleus. Rather than a standard 2D understanding of atoms, we now know that electrons are very much affected by probability, teaching us that the universe is random. Alongside physics and chemistry, quantum theory predicted the existence of antimatter and explains radioactivity. The implications of quantum theory are wide-ranging, from practical applications in X-rays, digital cameras, night vision goggles, and even quantum computing. We have our understanding of light and electrons to thank for, and all the modern physicists that made it possible.